Welcome back. Let's do energy in mutual inductance. Pretty easy problem, just fiddling with the equation and the signs. So we've got two of these dudes in close proximity, so their magnetic fields affect each other and they are mutually inductive. There's this mutual inductance M between these two guys. They also have their self-inductance, L1 and L2. There's currents going through each one of these guys. There's I1 here and there's I2 here. And there's an associated voltage, V1 and V2. And just as a check before we go any further, the current here is going from plus to minus. That agrees with our self-inductance reference for our formula, so that's good. We're not going to have any extra negative signs floating around. Likewise on here, the current direction goes from plus to minus, which is also agrees with our formula for self-inductance, which by the way is V equals Li prime, given an inductor with a current I going this way and a voltage V going that way. All right, this is self-inductance. Mutual inductance, just as a review, mutual inductance is two inductors. You got a guy this way. Okay, so there's a voltage rule and there's a energy rule. This is an energy problem, so I don't want to, I was about to draw the voltage rule here, but let's just not do that. All right, so I've got a couple of dots on here. Now there's a dot convention for energy that that's what this problem's about. So let's keep working this. So we want to find, this is given all of this stuff, given this thing. We want to find, here, let's find the total energy when I1 is 6 amps and I2 is 9 amps. So what happens when they're both positive? So we're not, so we have a formula for that. So the total energy in a coupled system right here, it's given by the energy in the first guy, which is that formula, and then the energy in the second guy, which is this formula. And then there's a modifier term. There's plus or minus M, I1, I2. And M is not given in this, well, here. L1 was given, this is 18 millihenries. L2 is given, this is 32 millihenries. And they give you the coefficient of coupling, which is 85, which is pretty good. It can be up to 1, up to 100% coupling. That's what they give you. So M we need to calculate, and M is given by this K root L1, L2. So M is gonna be 0.85 of root 18 times 32. It ends up being 20.4 millihenries. Okay, we can solve this thing now. So W on the total energy for these two currents is 18, and then you got 6 amps, and then you've got the 32 millihenry, and you've got 9 amps in that guy. So those terms are always positive. It's just I squared. It doesn't matter if I is a negative value, you're squaring it. But this guy here, okay, could be positive, could be negative. And that's really what this problem's about. So they're just going to try and confuse you in this thing. I'll do my best to not confuse you. But the third term is 20.4 times 6 and 9. And then the only thing you need to worry about is the sign here. So the sign, we use the dot convention, and you could even draw a little picture. You've got an inductor and a dot, and an inductor and a dot, and we've got 6 amps coming into the dot here, so 6 amps coming into the dot, and then 9 amps coming into the dot. So the rule is if both of the currents agree, then the term is positive. So both currents into dot, and I call that agree, because they could both be leaving the dot and that would also agree. That's the way I remember it. So it's plus, and if you wanted a value on this, which is almost beside the point, but you get 2.6 or 721 joules is what you get. That's the problem. What if we, work it with a couple of different currents? What if the same problem, but what if I1 were minus 6 amps and I2 were minus 9 amps? Then what? It would all be the same except for the sign on that last term. Oops. It ends up being plus because it's 20.4 minus 6 and minus 9. So they, the currents agree. If you drew the picture, now, here they're really just trying to confuse you. So you could draw it this way. If it's negative, then the arrows go in the other direction. Just do that. Get rid of the negative signs and just flip the arrows. And then so here you could say both currents are out of the dot, so they agree with each other. And so it's going to be positive. So that's what I suggest you do. And on the homework, they're going to flip these. You're going to have a negative and a positive. So what I would do is just draw the arrows with positive values. So if it's a negative quantity they give you, then just flip the arrow around, right? And the other two cases are, they're going to disagree with the dots, and so you're going to have a negative term on these things. All right, that's just playing with this and playing with the dot convention on energy. And one more reminder, don't forget, for mutual inductance, there's a dot convention for energy, and then there's a separate dot convention for voltage. Two different things. Don't get confused. All right. See you later.